and welcome to the Time Honored Tradition, Jacqui Romero.
Thanks, everyone. Yeah, okay, so we're going to do the second part of the lecture. I told you yesterday about what I think is quantum. I introduced the uncertainty principle. I think our future will really involve a lot of quantum technologies. Hence, I say the future is uncertain. And I think that's very good because we've got some really, I think, revolutionary quantum technologies that will affect us in the next few decades. So let's bring up the sponsors again. We've seen that yesterday. Okay, I just want to review what we had yesterday, the shirt that I have. So yesterday we learned about the qubit, which is the quantum version of a bit. We learned that it's a superposition, not just simply a 0 or a 1 like the classical bit, but a superposition with complex coefficients. And we learned about entanglement. This is, for me, really the quintessential quantum phenomenon. Entanglement doesn't have a classical counterpart. And when I was younger, I thought the most surprising thing was the correlation, that black goes with white and vice versa. But then later on, I thought, actually, that's not the most surprising thing. The most surprising thing really is that the property of one object cannot be defined, measured outside what happens on the other part of the object. I thought that was just really fascinating. There are no, like our common sense doesn't have objects like that because we don't operate in a world where we see that. And I think that's really part of the attraction of quantum physics for me. It's this very mind-boggling things. Okay, so I want to continue today on a more practical side. I want to tell you about different quantum technologies that already exist. I want to give you a taste of quantum computing. I know some of you have actually read about quantum computing from the questions you were asking yesterday. It is a very big, active field. I just want to give you a taste of what it could do for us. And then finally, I want to spend maybe half of my talk to show you something that some actual research that I do in my field. Okay, so let's start with quantum technology. So this year is the International Year of Quantum Science and Technology. It's UNESCO declared International Year of Quantum Science and Technology. And we had an opening ceremony in Paris in February. I was there. I was very excited to be there. We've got like Nobel winners in the field. In that one place, I think there were 4 of them that day. There were many representatives from different countries all over, like really from Africa, Asia, Europe, North America. It was a very global, party. And it's very different from when I started my PhD back in 2008. Like I remember one of my professors in the Philippines, when I told him I want to do a PhD in quantum. And he asked me, are you sure? Because it looks like it's a fad. And he couldn't be any more wrong. I think that it has really grown to, even for me as someone really interested in quantum, this is unexpected where we are. And that could only happen with the rapid development in many fronts. So it's really a very exciting time for quantum. And I want to share that excitement with you. With some quantum technologies that are already out there. So we have quantum communications, which will lead to secure communications. Because when you have quantum communications, you actually are able to detect when there is somebody listening in to your communication. And then we have quantum sensors, which provide sensing capabilities that we won't be able to do otherwise. I'll give you an example later. And then I want to focus on a little bit on quantum computing because that gets a lot of hype these days. So let's just try to digest that a little. Okay, I want to start with quantum communications, but I want to go back a little bit to cryptography. So this is have you heard of the Burnham cipher? Who's heard of the Burnham cipher? So the Burnham cipher is something like this. I'll give you an example. I'm sorry for the political color, but this is a Burnham cipher that Che Guevara used with Fidel Castro in the 1960s when the Bolivian Revolution and all that political unrest was happening. So in the Burnham cipher, each letter you represent with some number. So that's the first row here. So this is the message that was that's the part of that's the secret that Che would not transmit to Fidel. You replace all the letters with the numbers. And then you got like these underlying the numbers, these underlying random numbers. They are the key. Now the key is known only to the two persons who are going to communicate. It is the secret. Okay? And then what you do is you add the message with the key. And then what you're gonna send to the messenger is this, the sum, the third line. Okay? So when the person receives the random number, because they know the key, they can subtract that key from the random number, and then they're gonna get this first row of numbers. So then they'll be able to decode what the message was. Okay? So the key in cryptography is very important. It's what you use to decode the message that was sent. Okay? Now, when people say quantum communication is really very broad. But the most popular protocols are the ones that involve key distribution. How do you share keys? In ordinarily, what you would do is you have a very trusted person. You write the key, like this is in the olden times. Okay, just say in the olden times. You would write the key. You have a very trustworthy person. That person gives the key to the other person, and then the key is secret. Like these days, we have many different ways to share keys. The RSA is one such one key distribution protocol. The first quantum key distribution protocol is this one from 1984, Bennett and Brazard. They are Canadian physicists. And this is actually really, if you think about it, simple. What you have here is a single photon source. So every time there's only one photon that goes out of that source. And then you've got the two persons communicating, we call them Alice and Bob. Okay? Alice prepares the photon, so she prepares the photon to be polarized into any of these directions here. So like choosing what the spin of the photon will be. Okay? So she's got these choices. And then Bob here on the other side can choose to measure on this, basis. So we call it like, let's call it measurement settings. So Bob can choose to measure either horizontal, vertical, or diagonal, anti-diagonal. Okay? And then, so Alice sends lots of photons. Bob chooses the settings randomly. And then after some time, they will get together. Alice and Bob gets together. Bob will tell Alice which settings he chose in measurements. And then they will compare the results. So as you would expect, if Alice and Bob chose the same settings, they will get, Bob's result will be as what Alice's preparation cost. Okay, so if Alice prepared a vertical photon and Bob chose to measure in horizontal or vertical, he will get the vertical photon. So you get a correct bit every time they choose the same settings here. If Bob measured in another setting here, like if he chose anti-diagonal, diagonal, and then Alice prepared the horizontal or vertical photon, Bob will get the correct bit 50-50, 50% of the time, right? Because if I have a diagonal photon and you have a horizontal polarizer again, there's a 50% chance that the photon will pass or not pass. So you get errors every time there's a mismatch between the two choices. But they get together so they know which photons they chose in the same basis so they can create. Okay, so it's that simple protocol. Now, where does the security of this come in? Like, why do we say it's secure? So imagine if you're the eavesdropper, you're Eve. Your strategy would be, as the photon is being transmitted, you intercept one of these photons. Okay, you get one of the photons from Alice. And then, of course, Bob is expecting a photon, so you have to prepare a photon to send to Bob, otherwise you'll be found out, right? But in quantum mechanics, there is no cloning, meaning there's no photocopying machine for quantum states. You cannot prepare a copy of a state that you don't know. So the best thing that Eve can do is to do a measurement of that photon that she has intercepted, and then prepare a photon based on what measurement she got. Okay? Now, the key there is that because Eve will have to decide on a setting, she will guess this setting, and you expect half the time she will get it wrong. So when she gets it wrong, prepares the photon, sends it to Bob, then Bob and Alice gets together, they will find that actually we are getting more errors than we should be expecting. So then they know that there was an eavesdrop. Okay? So when articles tell you that quantum communications is unhackable and all that, what that means really is that in real time, somebody can hack, but the persons communicating, they will find out. The eavesdropper always reveals themselves through this quantum mechanics that's happening. And it is actually a very active field, like quantum key distribution, quantum cryptography is full of many work to show statistical analysis as to what is the threshold for you to be able to say that this channel was secure, this channel was eavesdropper free. I don't do that. I do the focus part. Okay. The quantum communications. Already. So by statistical analysis, you can find it there. Now, real-world demonstrations of this are plenty. I'll give you the most impressive ones. In 2017, there was the quantum key distribution. At that time, this was the record, intercontinental quantum communication between China and Austria. So this was mediated by the satellite missions, and they used ground stations, like the same stations that astronomers use to look at the stars. Okay? They send photons from the ground station to the satellite and back. That's 7,600 kilometers altogether. And they used that to do a video conversation between the academies of science of those two countries. It was very slow, like the key was kilobytes per second. Because as you can imagine, if you're sending something through photons through free space, there's a big chance they will be lost. So it was very slow. But nonetheless, I thought that was very impressive. This was BB-84 Intercontinental range. Now, 2025, this is hot off the press. This is work between scientists in South Africa and China. Now we have beaten that record. Now we have done intercontinental quantum communication over 12,900 kilometers. So this is, I forget which city in China, but in South Africa, it's Stellenbosch. So it's even farther. And they've done some technological improvements. One is that, remember I showed you the ground stations that was used in 2017 were the astronomy ground stations. You've got like the big telescopes and all that. This year, they managed to do it with portable optical ground stations. So it's like, a kit that you can actually travel with from one place to another. You don't need to bring the big telescope. So they did that with portable ground stations. It's 10 times lighter compared to the big ground stations, big stationary ground stations of 2017. And the other thing is that they used microsatellites. So VISIOS was a very big project, 250 kilograms of the satellite. It's actually China did it only for quantum B distribution. That was impressive. But it's now even better. It's 10 times lighter. So we can make these more flexible with these improvements. Like I just show you what's inside the ground station. As you can see, there's really nothing so special. We've got mirrors, beam splitters, detectors. It's just a lot more stable and better. Okay, so where will this lead us? I actually don't know. To be honest, quantum key distribution, if I ask my quantum cryptography friends, they tell me there's no business case for it. And then I think, well, if there's no business case, why are people doing it? I think from a technological perspective, it's very interesting, and I think it's really possible that in the future we will have constellations of these microsatellites and these portable ground stations, making up networks where we need them to be. So watch that space. There is another QKD protocol that I will not talk about. That's the EQUS2025. That's based on entangled photons, distributing entangled photons. BB84 was just single photon. This one is based on entangled photons, but I'll leave you the research lab. Maybe you'll find out about the monogamy of entanglement. It's called monogamy because it means when you have two entangled particles, and one of them meets another particle, like a third particle. If one of them gets entangled with this one, the entanglement between them and the original pair will actually decrease. There's a trade-off. And that's somewhat where the security of the T91 protocol comes from. Okay, quantum sensing. So quantum sensing, I think, is the application that is nearest to economic value, if not already. The UK has a big program on quantum sensing. So this is just one example from the University of Birmingham. They've developed what they call a gravity gradiometer, and that's used for mapping what is underground. So when you have a cloud, when you have atoms, it turns out they're actually very sensitive to little fluctuations of fields. And I'm not an expert, but this is what's inside that gradiometer. To me, it looks like instead of splitting light, they're splitting clouds of atoms. So this is think of it as your atomic beam splitters. And then they interfere those clouds of atoms. You find out how many of the atoms are in the excited, how many are in the ground state. And then from signals like this, you can map out what the underground is. There's going to be more information here. I think they actually have a company now. There's a...
Is that because the cloud of atoms is really sensitive to tiny changes in gravity? Which tells you about what's under the cloud. Is that the gravity?
Yeah, I think so, yeah. It's very, Actually, in Australia, I actually have colleagues who used atomic clouds as a weighing scale. It's funny actually. Okay, big rocks. I didn't think about this. When you have a big rock, it's actually hard to weigh how heavy that is. So this in the context of mining. Australia is a very big mining company. How do you know how much have you mined from the ground? Well, you put them on the chalk and somehow you weigh them, but there's not a big enough weighing scale. So it's actually very error prone. And there's research now to show that you can actually use atomic quantum physics to do that more accurately. Another kind of sense. Okay, so those are the first two quantum technologies. Now I want to talk about quantum computing. This is getting a lot of press in recent times. The messages I want to leave with you is that, quantum computers, they are not versions. They are not just faster versions of classical computers. Quantum computers have advantages for very specific problems. So it's not like everything will be made better by having a quantum computer. It's actually very specific class of problems. And two of those are these. One is the factoring of big numbers. We've already heard about this yesterday, Shor's algorithm. So as you can see, the best classical algorithm, the runtime goes like this. For Shor's algorithm, the runtime goes like this. So it's much faster. Another example is what's called the Grover algorithm. Grover algorithm is if you have an unsorted database, so you have no idea where the entries are in that database, you can have a classical algorithm to find a particular item in that unsorted database. The resources will grow like this. For Grover algorithm, there is a quadratic speed up. You have Grover algorithm just this much time. So these are the first two problems which had like provable advantage. And when I say provable advantage, it's really the physicists and the mathematicians like really showing you that okay, we can use all these mathematical tricks and this is gonna be true. Okay? Grover's algorithm and Shor's algorithm have been demonstrated, but they're nowhere near economically interesting cases. They're more like proof of principle demonstrations. Current quantum computers are plenty. IBM has one. Microsoft is looking for qubit. IBM. I think this from the Google roadmap because they're doing some really nice work recently. So Google quantum computer is based on superconducting qubits. And in their roadmap, they started with 50 qubits on one chip. They are currently over here where they can put hundreds of qubits in one chip. They want to go to this where you've got millions of qubits in a facility that looks something like this. Okay, so this is a person here. This is going to be how big that computer is going to be. Okay, so these are really big numbers. Like you need millions of qubits to do what's called error-corrected quantum computer. Error-corrected meaning hopefully it will be economically useful. Not just physics interesting. And I would say I think they are on track. Google has, they want a very good lead. So yeah, we're here. I think we are about here. There are many technological and basic science problems that we need to overcome before we get to that million scale. Why do you need a million? Well, let's go back to Shor's algorithm. So this is an estimate of the time to factor an L-bit number. Okay, so say 1,000-bit number here. All the red is what Shor's algorithm, what the performance of the Shor's algorithm. But take note that is Shor's algorithm that runs on 2 times L squared logical qubits. Okay, so it's even more than a million. So as you can see, you actually need a very, very big computer in order to compete with what our current computers can actually factor. Okay, current computers can do this. Like they can do this. So if you ask me, it's really a long time before we're gonna see a computer that can do Shor's algorithm. And here's what the experts think. So this is a report that came out in 2019. Like they asked experts, what's the likelihood of a quantum computer being a significant threat to cryptography as we know it? And as you can see, they're all like in the decades away. But we might be wrong. So watch this space again. But like, don't be scared, just so scared just yet. I think it's gonna be a long way away. Okay, so that's one application of a quantum computer to break cryptography, which doesn't sound so benign. I'm gonna give you another one, which is really the original motivation for quantum computers. Shor came in 1994. Feynman in the 1980s was already saying that nature is quantum. If you have quantum systems, you better make your computer quantum mechanical. And that is a very difficult problem because as we know, quantum systems, they're very susceptible to noise. And as you can see from the Google roadmap, it's actually very technically challenging. So we're still on our way there. We have quantum computers, but they are not useful. And when I say not useful, there is nothing I will do in a quantum computer that I cannot do with a classical computer right now. And we are working towards a useful quantum computer for problems like this. Like quantum chemistry is really the killer application. Quantum chemistry is the killer application. So this is just one example of a carbon capture catalyst. I didn't put the elements because I just cannot pronounce it. The important thing is this is a molecule that if you can produce, can capture carbon from the atmosphere. Okay? Can help us with global warming. And right now we cannot predict the configuration of these molecules because it's just impossible to do full configuration modeling of a molecule that has 119 atoms. A quantum computer can do that. With the current technology that we have, we can do that, but like after a decade and with 10 million qubits. So it's kind of depressing. The game now for quantum computer experts is to go to this region here, where we really can do useful quantum chemistry problems within days and within maybe hundreds of thousands, millions of qubits. So we are a long way away. That's what we need younger people for, because I think there are really a lot of problems that you yourselves will be solving to make that a reality. Okay, I want to end this section with DiVincenzo criteria. So DiVincenzo is a physicist who wrote what does it take to have a quantum computer in a very abstract way. Okay, so he's got these 7 things that a quantum computer needs. The first 2 things are you need qubits. You need to be able to generate your qubits. You need to be able to define what's the initial state of the qubit. The next 2 things are for when you are manipulating the qubits, for processing. So, third, long relevant decoherence time, meaning the quantumness of your system stays for a long time. And then fourth, a universal set of quantum gates. In the same way that in classical computer we have an AND gate, OR gate, we have those gates in quantum as well. They're different, but you need a way to process those qubits. And then the fifth is the measurement and detection, like what Bob does. You need to be able to detect your qubit state. And then 6 is to be able, 6 and 7 is to be able to transfer your qubit from like one computer to another. Now, the 6 and the 7 criteria, this is actually where using photons would really help. Because, as much as Google can work on their technology, they will never be able to transmit a superconducting qubit over kilometers. Photons can go through kilometers of fiber. They will get lost, but some of them will go through. So this is really this is why I'm actually putting my bet on a photonic quantum computer. Because if you have a photonic quantum computer, transmission from one computer to another will not be. Okay, so thoughts for you when you design your quantum computer in the future. Now for the remaining time, I want to show you actually what I do. Okay, so I'm an optical quantum physicist. I play with photons, and recently I have been transforming my big optical experiments into smaller optical experiments. Like in the same way that, when we had the first computer, it was this size, that's the ENIAC from the 1930s. And now we've got like an iPhone, like in my pocket, with so much more computing power, very small. So, from that scale, really revolutionized a lot of computing. And it's going to be the same for quantum computing. All the technical roadmaps point to integration, to making things smaller. Because if you do it on an optical table, so like in an experiment like this, by the way, was a COVID experiment in China. There's a lot of optical elements there. It's maybe 3 by 5 size. You're not going to bring that out to the field. It's just going to be so inconvenient. So we need to put everything on the chip. And that's what I do. Like half of my research group now does integration on chip. Because going on chip improves your scalability. You can have more information processing. Improves stability because you don't have a lot of moving components. And you can really go to applications that you won't otherwise be able to do. Because who will bring an optical cable to a mine, right? Like this, it's just going to be very hard. And this is a very active field. So as you can see here, there's a roadmap. This is actually the history so far. So we started with, there was a Shores on chip in 2010. These days, I don't know what's the direction for sure. But we have a lot of components now that we can do, put on the chip. So my job these days is to think of how I can put my photonic units on the chip. So you've seen some of these yesterday, like different properties of photons. My favorite is shape. As I said yesterday, I like playing with light that looks like this. The shape is interesting because it's kind of a sweet spot between having many modes into one waveguide and the complexity of your chip. So let me back up. So this is packed. So when you have a photonic chip, the analogy to the wire where the electrons go through is called a waveguide. It's like, think of it as a very thin piece of glass and the photons go through that. It's like their highway, okay? Now, your photon it can be blue, red, yellow. So in that one path, you can have 3 colors, like 3 states going through one wire. You can also make different shapes. So you could have these different shapes traveling through one wire. So going to QDIS improves the information capacity of the wires in your photonic chip. So in our group, we make components that would manipulate those shapes on chip. Now, how we do that in practice is something like this. Well, traditionally, the multiplexer is a device where if I have a photon here that can be of any of these different shapes, the multiplexer will, like this device, is a demultiplexer. The demultiplexer will make them go out different ports like this, okay? As you can see, it's actually very regular. like it's almost like somebody drew that. But it's actually a very tedious process to design it because you do it from bottom up. What you actually do is you try every possible width, every possible angle of the curve until you get a device that will actually do this. Okay, it's very tedious. Now in our group, what we do is instead of bottom up, we do actually top to bottom. And what I mean by that is, say I want a device that separates the blue from the red. What I'll do is to design by specifications, like for the FLC. So I say, okay, I will have a piece of silicon. I will define an input and output. And I'm going to tell the algorithm, okay, I want blue to come out here at the top, red to come out here at the bottom. And then I let the algorithm iterate until I get a design that looks really irregular, but actually does what I wanted to do. Okay, so it's compared to the one I showed earlier where the features are very regular. This one is really wild, but it's small and the function is actually as I have designed. It's a very recent development, like recent maybe about 10 years, and it's only now actually that it's been being more widely used for quantum. So photonic inverse design, I will not bore you with so it's machine learning. It's machine learning for those of you who like machine learning. It's gradient descent. So you just have an algorithm that simulates how the light goes from this end to from the input side to the output side, and then we iterate until we get the cost. So the cost function is defined according to the purpose of the device that you are designing. You do that over and over, and then you get a device that does what you want it to do. So for example here, I want to design a device that does this multiplexing. So this is the states that I'm trying to manipulate here. So if the shape is TE0, if the shape is, okay. So maybe it's easier to understand from this direction. So if I have TE0 this way, I want it to go out the top port. If I have TE1, I want it to go out this bottom port here. Okay? So what I'll do is I'll simulate a device. I will specify I want the device to be 3 by 3 microns. I just divide it into 40 nanometer by 40 nanometer pixels. I will throw the Maxwell's equations onto my computer, and then it will simulate as it's trying to randomly assign the shape of the square in the square region here. And what you find is that it actually works. I'm gonna show you how it looks like in practice. So this is our cost function, and this is iteration. As you can see, it actually doesn't take a long time to get to a good performance of the cost function. And after like about 100 iterations, we actually get a device that looks like this. If I were to simulate the light going through that device, it looks like this. So as you can see, TE0 goes at the top, TE1 is TE1, I guess that's splitting here in the middle, it goes to the bottom. So it works, but we don't understand, actually, okay, it's physics that governs the electric field here, like the photons here, but it's nowhere near what I would have designed intuitively. And we've tested these devices. We get very good transmission through them. And crosstalk just means like how much error do you have? And that's not a lot. It's very, very, very small. Okay, so we design those devices. We also fabricate those devices. So these are actually actual fabricated devices. As in, we get a beam, very strong beam of electrons. We like draw the pattern on the silicon, and it looks something like this. So as you can see, we can recreate the design very, very well. Like with an electron beam lithography that I think has 10 nanometer, 20 nanometer resolution. It's very, very good. And we get very good transmission through the device, so we're happy. We test them in the experiment, and we get results like this. So as you can see, there's very good match between the simulations and this. Okay. So multiplexers we've done. We've also done mode beam splitters. Mode beam splitters is just another device which splits one shape into two shapes. So TE0 becomes TE0 and TE1. TE1 becomes TE0 and TE1. So it's something like this. So as you can see, there's going to be two possible shapes at the end after the beam splitter. And we've simulated them. They work very well. And we created them as well. How many minutes do we have? Another 10 minutes. Okay. I want to show you a cool experiment. So like you might ask me, why did you make multiplexers and beam splitters as the first components? And the answer to that is because there's this very cool experiment from the 1980s called the Hong-Ou-Mandel experiment. And it shows you quantum behavior of the photons in a very fascinating way. So this device is called a beam splitter. A beam splitter splits the photon into going this way or this way. So there are two possibilities for the photon to exit this way or this way. It also has two input ports. The photon can enter through here or through here. Okay? What Hong-Ou-Mandel have realized is that if you have two photons that enter here, and you cannot distinguish between the two of them, like they're called indistinguishable photons, as in every property is the same, they do something really weird, like they bunch. What does that mean? So I have two photons coming in here. This controllable delay just changes the time that the photon enters the beam splitter. Okay? The two photons are the same in every property except for when they enter the beam splitter. And in that experiment, what they discovered is that as they are changing the delay, this happens. So the y-axis is called the coincidences. It's just the number of photons that arrived at the same, that arrived on these detectors at the same time. So it's like every time you ask yourself, did I get a click on both these detectors? So meaning the two photons that entered shows different detectors to go to. When you go to this zero delay, meaning the photons arrived at the same time, you get a very signature dip on the coincidences, meaning only one of the detectors click, which means that the two photons are on either of these detectors, on just one of them. Okay, so coincidences drop. That's called the Hong-Ou-Mandel dip. It's a very signature property of single photons. You cannot describe it using classical physics. So you really need quantum physics for this. And it was really the start of, it's the start of many interesting applications for quantum photonics. Now, I named a beam splitter and a multiplexer because I wanted to do the same experiment with transverse modes. I'll just show you. So this is a Hong-Ou-Mandel experiment. Oh, sorry, before I do that. You might ask, like, why does that happen? Why does Hong-Ou-Mandel interference happen? And the answer to that is quantum mechanics. A beam splitter, you can describe it as in a quantum mechanical way through we call it creator and annihilation operators. They don't have classical counterparts. But what you find is that when you do that, the probability amplitude, the possibility that both photons get transmitted and both photons get reflected, they cancel each other. And what you're left are only these two possibilities when they both go to the same detector. It's really fascinating. So the 1987 was Hong-Ou-Mandel on path. Nowadays, there's Hong-Ou-Mandel on frequency. So as you can see, there are different colors here for the two photons. We are trying to do it with our transverse modes, with the shapes. Like in this experiment here, only that their devices were these regular looking things, and they're a bit larger as well. They're 170 microns. So we wanted to reduce that footprint, and we wanted to show that with this wild way of designing your components, you could still get that quantum signature. So that's what we did. We made a Hong-Ou-Mandel device. We stringed our multiplexer, we splitter the multiplexer, and then borrowed some really good photons from our friends at Griffith University. Like, we literally drove our chip to their lab, and then we stayed there for a month. We said, we crashed their lab a month, we'll just take data with our chip. And then we got these really nice results. As you can see, we got the signature dip, and I'm very proud, it's almost 100%. If your experiment was perfect, that number would be 100%. We got 99.56%, which I think is really record for transverse modes. It's one of my favorite results in recent times. Yeah. And then what's nice about our devices as well is because when we are designing it, we are actually exploring this big parameter space of the different designs in our silicon. It's very robust to fabrication errors. So the thing is, when you're doing electron beam lithography, sometimes if you wanna have 20 nanometer circles, sometimes the EBL will make you 22 nanometer circles. So it can have deviations like that, but inverse design is robust against those deviations. So this is actually some other devices. We have a sample of devices that we have created. So same design, we just have multiple copies of it, and then we find that actually all of them is very nearly 100%. So that's really very promising. Okay. Then we said, okay, we can of course do 1,000 devices with like different fabrication biases. So we just simulated it, and we got very good results. So as you can see here, we're saying even if you miss by 5 nanometers, you still get greater than 90% visibility. If it's greater than 10 nanometers, it's still okay. You get 50% visibility. Like 50% is actually an important number, because over 50% is when you can really say this is a quantum phenomenon. Okay, so that's it. I think that's all I have time for. So I hope what you take home is that one, quantum technologies are out there. They're outside the laboratories. When they will give economic value is a question mark, but I hope you will be part of that journey. If you're looking for a problem to solve, quantum technologies is there. Quantum computing will change the world, but not just yet. There's a lot of science to do. And lastly, I showed you some stuff from my lab. Photonic inverse design, which by the way is not just for quantum, it actually started in classical photonics. I think it's a very interesting approach to designing photonic components, and we've just shown that it leads to devices that can actually support quantum phenomena such as the Hong-Ou-Mandel. Okay, that's it.
Thank you so much, Jacqui.